Okay, so good morning, everyone. I think there's quite a few people who are missing, but it's okay. I think it's raining, so okay. So today we're gonna continue with tree methods. So specifically, we are going to look at random forest that you've already seen in the complementary class. So today we're going to look at random forests, and there's this little bit more fancy regression model called what is it called? MARS, which stands for multivariate adaptive regression trees. So that's the second method that we're going to look at, and the third method that we're going to look at is also probably familiar to you guys, which is called support vector machines. So you might have seen them. I don't know how much of in-depth conceptual insight you've gotten for either of these three methods, but today we're going to try to understand them in a little bit more detail, so you're more confident with what approximations or what assumptions each method is making. Okay. Any questions before that in terms of assignments or exam or project?
Maybe just an overview of what we need to write on the project report or what is expected. Also compared to, so I see that in the grading guidelines, they say compared to the previous report, like I don't want to see this and that. And so it would be interesting to know in the last report what you don't want to see compared to the one we have to submit, because otherwise,
Okay, so this is so Hasing has given guidelines on what is the delta that needs to be shown in the second report. Is that what you're referring to?
Yes.
So Hasing has posted some guidelines on what needs to be in the second report. Is that you're asking? Okay, so he's written what more needs to be added to the second report. Your question is what is the delta from the next final report? It's a good question. Let me get back to Hasing because he's deciding on the milestones. So I will ask him, and I'll ask him to post something on the web, on Slack. Sorry. Any other question? So assignment is fine. So actually, I think one or two questions in the assignment require random forest that we're going to look at today. But you might have already seen random forest in some other course. So if you have already done the assignment, good. You don't have to wait. Spend more time here. On these parts. Okay, so.
Sorry, just one other question. In light of the grades from the midterm,
Yeah.
how is the final going to be?
So what do you think? The midterm grades are good or bad?
I have no visibility on the average, so I don't know.
Yeah, and I couldn't look at the average before coming here. I think the students did fine, but I was hoping for a more concentrated distribution of grades. It seemed a little bit more, more broader, had a higher variance, empirical variance. So the level of the final probably will be similar or easier. Those two would be the options. Huh? No, it's not going to be cumulative. Yeah. We're just going to kind of try to test for the understanding of the material after the first 6 lectures. Okay. There's no point burdening. There's no point remembering everything we did. Several months ago. Okay. Any other questions? Okay. So let me write down the 3 methods. The first one is random forest. Now all these methods have very exotic and interesting names. So we'll try to kind of understand why each method has certain phrases in their names. And just to give a big picture, we started the class with K and N on one side and linear model, linear regression, I guess. on the other side. So this was making a strong assumption on expectation of y given x is equal to x, right? That it's linear. And here KNN was actually just approximating this using some empirical average, basically 1 by k times an average of yi such that xi is one of the k nearest. And in between there are several methods, and these three methods are somewhere in between here. Okay, that's the idea. So trying to, kind of deal with cursive dimensionality, but not making really strong assumptions about your regression function. Okay, that's the big picture. So before I introduce random forest, I'm going to use the acronym RF here. I'm going to describe another very intuitive method called bagging. Okay, and it's again a phrase. It's just a shortened version of bootstrap aggregation. Okay. And the idea is pretty straightforward. It's saying you anyway have some data Z from which you're creating capital B copies of Z star, Z star B. Okay, so Z star 1 all the way to Z star capital B. Okay. So these are the bootstrap samples. You sample with replacement, and actually, although there is a hidden choice of how many samples you wanna how many observations you wanna create in each bootstrap sample, let's assume for simplicity that if the number of observations here is n, let's say each bootstrap sample is also has number of observations n. Okay, but you could potentially change it, and changing has different consequences. We'll not go into the detail here. Okay, and for each one. And this we have already seen before. For each one, we could have created a model, right? Right, using that data. Bootstrap aggregation, all it's saying is make a prediction, final prediction f hat of x as just the average. Okay. So for any given x, just I take the average. Okay, it's a very straightforward idea. And so why do you want to do this? Because maybe this reduces reduces some, so you remember we were doing bias variance trade-off of models, and there's, let's say, think of mean square error. We broke that down into a bias square term and a variance term. Maybe this has some impact on one of those terms. You want to try to the hope is that this averaging of many different classifiers or many different models built from bootstrapped samples of the same data can influence one of these terms. Okay, and specifically what happens is with this type of averaging, the bias term doesn't change. Okay, so each let me just write it down. So if you remember, I'm roughly going to write mean square error is basically, I won't say equal. Okay, it's equal to bias square plus variance, and these are actually for the model, f hat, right? So the bias of f hat is going to be the bias of the same, if you had built a model using just z, you would get one model, right? The bias of that model and bias of this model is going to be the same. But what could potentially get affected is the variance of the model. It could decrease because you're doing some averaging. Okay. And I won't illustrate it in terms of the model context, but I'll just illustrate that that you already know this fact for a simple collection of independent and identically distributed random variables, right? So if you know, for example, that let's say x1 to should I use x? Okay, let's say w1 to wb are IID random variables. Okay, so IID just means the first I guess just means independent. So probability of x1 comma x2 is just splits into x1 times probability of x2, right? And identically distributed just means they have the same distribution function or the density function or the PMF, whichever is the whatever type of random variable it is. And if they're IID, then the variance of 1 by b of sum over little b of wb is just let's say if they're IID and they have a finite second moment, as in they have a finite variance, okay, let's say it's sigma square. And then this is just going to be equal to any ideas? Huh? So the options are sigma square divided by b or sigma square divided by b square. Okay, yeah. So to see that variance of independent random variables just splits. Okay, so variance of w1 plus w2 is the variance of w1 plus variance of w2, and if you have a coefficient 1 by b, then it comes out as 1 by b square. Okay, so let me just expand this. So it's just going to be variance of wb sum over b, and each one has a coefficient. I guess let me write the variance of right. This is just so this is what I said. If they are independent, you can split it this way, and so each one I said was identically distributed. So it's just the summation has b terms. So b times the variance of, let's say, w1 divided by b, and that is b times b square times sigma square. Okay, because if you have a constant coefficient, constant multiplier to random variable, then you can square it and then look at the variance of the random variable itself. So that's why you get sigma square by b. Okay, so there is variance reduction. Basically, I'm saying that if you have independent random variables, you take an average, then you have smaller variance. Okay. This is nice, and hopefully bagging is also trying to do something similar, but the catch is that bagging is using samples which are all correlated, right? They're all sampled with replacement from the same original data, z. Okay, so that could be an issue, and that's why we'll actually jump into random forest in a few minutes from here. But just to see that, let's look at another example. Let's say w1 to wb are identically distributed, not independent. Okay, and the correlation between wi comma wj is, let's say, rho. Okay, so does everybody understand what correlation is versus covariance? Who doesn't doesn't recall what the definition of correlation is? So let's say correlation is this. Then I'll write down a fact. We won't kind of derive it here, but if random variables are not independent, okay, then the variance of their sum, okay, sum of w I guess B. Let me use the same thing, divided by B. Right, that was the quantity from before. Yeah. So this, anyway, we know that, at least the coefficient term, just a constant number, just comes out this way. So variance of sum over B is equal to 1 to B of WB. Now this is what is interesting, and this variance, there is a, just take it as a fact. Actually, you can derive it simply, but I'm just going to write it. This is equal to sum over B equal 1 to B of variance of WB plus 2 times sum over B1 less than B2. Okay, let me actually explicitly write it. B1 equal to 1 to B sum over B2 is equal to 1 to B1 of the covariance of WB1 WB2. So this is just saying, just look at, if you think of I comma j pair, there are n square such pairs, right? I mean, you can think of it in terms of a matrix, and all I'm saying is just look at the entries in the upper diagonal or entries in the lower diagonal. I'm just saying don't double count, so that's why I'm saying okay, actually, so only take think of excluding the diagonal elements of a matrix and only looking at the upper triangular or maybe the lower triangular. It's the same. Okay. So think of it this way, right? If I want to take an entry here, let's say this is the B1 throw, and let's say B second column. Okay. All I'm saying is that these indices, I'm just gonna ensure that they only cover the lower triangular part of the matrix. Okay. In terms of counting, the total number of entries in this matrix is B square, right? For every every B1, B2, I can take a pair, so there's B square. I'm just saying count just the lower triangular, so that's going to be B times B minus 1 by 2. Okay, it's going to be n choose 2. Okay, so this is just a fact, and the reason why I wrote this down is to kind of understand in our setting. Okay, we just said the correlation is rho, right? And so the covariance is going to be for identically distributed random variables is going to be just rho times sigma square. Okay, so you know that correlation and covariance are just scaled versions. Correlation is just covariance divided by sigma, the variance of, or the standard deviation of the first random variable and the standard deviation of the second random variable. Let me just write it down actually. What did I use? Okay, I should maybe covariance divided by square root of the variance of Wi, variance of Wj. So this is just the definition of correlation. And so in our case, just I want to use these two facts. I guess this is also a fact, or just a definition actually. I just want to use these two facts and kind of get an idea about how much is the variance reduction I'm getting when I take an average when random variables are correlated. Okay, that's all. And so just write that down. Variance of 1 by b sum over little b of w little b's was 1 by b square, right? And so I just want to plug this formula in, which is going to be sum over b is equal to 1 to b of variance of wb, and we just said variance of wb, let's say they are identically distributed, so it's going to be, let's say, sigma square times b, because there are b terms there, right? This has b terms, plus 2 times I'm doing a double summation, and I just said the number of double summation terms is b times b minus 1 by 2, right? Because each covariance, since they are identically distributed, each covariance term is the same, and we just said covariance is correlation times square root of the variance times variance, and variance is the same for both of them, and it's square root of them, so it's going to be sigma square. Okay, and you can just simplify this, so it's going to be sigma square by b plus b minus 1 by b times rho times sigma square. Okay, so let's see. So it's going to be sigma square by b plus rho sigma square minus rho sigma square by b. So I just split the second term into 2 parts. I can do that. Right, and I just want to stop here and just point out that one of the terms doesn't depend on b. Okay, and so if you have b is equal to 1000, there is some variance reduction happening because of these terms, but there is a term which doesn't depend on b, and that depends on the correlation between the random variables. So if the random variables are highly correlated, you will not be able to reduce the variance. There's a lower bound. Like if you turn b to infinity, then you'll still have this term rho times sigma square. Okay, and rho can be as close to 1 as possible. Then you have really not reduced any variance. Okay, so something like this can come into picture when you're doing bagging. So you're averaging a bunch of predictors, right? Think of them as trees. So you created a tree from every bootstrap sample, and let's say it's a regression tree, and then with that you're making a prediction. You can take an average of every different tree that you got because of different bootstrap samples, right? Bootstrap samples. But because the trees were constructed using data, which is, ultimately there's one piece of data from which you got the bootstrap samples, the trees will be correlated, and so you'll not be able to reduce the variance. And so you'll not be able to kind of attack the MSE, the bias variance term you had, too much, right? And that leads to the idea of random forests. Okay. So it tries to improve on bagging. So of course bagging you can do with any model, like you don't have to concern yourself with trees. Here we're going to just specialize to trees. Okay, so there the f hat star b's that I had written symbolically, they correspond to trees, let's say. But you can use bagging for other models, right? So you improve on bagging by reducing correlation between trees. But if you want to reduce correlation, sometimes you may end up increasing variance itself. So the whole point of bagging was to reduce the variance term and the bias variance, decomposition of the mean square error, for example. But if you want to reduce correlation, maybe you are doing the opposite, right? You are probably increasing the variance of the second term in the bias variance decomposition. But there's a fine balance, but we will not go into the detail of how much variance is going to get increased. But we'll just touch on the idea that random forests are just trying to reduce correlation. It's trying to reduce the row term. For example, in the previous stylized example. Okay, and so I'll just write down the the key step with which it's going to reduce correlation, and it's a very straightforward step as well. You might have already seen this in the in 572, but let me just write down the algorithm. Okay, so random forest for classification. So for b is equal to 1 to capital B, you get get z star little b. Okay, and get a tree T subscript B by recursive partitioning. So we saw recursive partitioning when we were describing tree methods last time, right? So it's just you have a node which corresponds to a region, and you want to break down that region into two parts, R1 and R2. So you just pick a variable, pick a split point, and just divide the region into two parts. And the choice of the variable and the split point just corresponds to maximum decrease in terms of whatever metric that you have. For example, you can have a mean square error metric, right? So let's say some points fall into that region. You're just asking how far is the average of those points compared to a constant predictor for that region. And then once you split, you'll have two different numbers because two different regions. So look at the points falling in one region, compare them to the constant corresponding to that region. For the second region, also compare them to the constant corresponding to that region. The total sum should be smaller. You have more degrees of freedom, of course the number will be smaller. How much will it be smaller depends on the choice of the split coordinate and the split point. Okay. That's basically the intuition for splitting. Recursive partitioning as before, but you do one thing at each split. Okay, which is so with an additional modification, and that's going to be you're going to choose m less than p variables at random to be considered at each split. Okay, so I said while building a tree you have to choose one of the p coordinates. Let's say p is the dimension of the input variable, so we have to pick one of the p coordinates, right? That's we greedily choose that, not greedily, sorry, we just choose that based on the reduction compared to the first the original region, a constant, split, you have two different constants, but the split is you have p choices instead of p choices, and we're just saying only choose among m choices where m is strictly less than p. Okay, and m is now a design choice. You can choose m to be 1, you can choose m to be p. If m is p, there is really nothing you're doing. But if m is really small, then you are really restricting your split choices. Okay. And so you got a tree. Where is this for loop? Let's see. Okay. So you got a tree, and then the for loop ends here, and then your prediction is just as before, f hat. I'm gonna put all sorts of superscripts and subscripts, but all it just means is b bootstrap samples, subscript rf represents I guess random forest is 1 by b of the sum over b is equal to 1 to capital B of pb of s. Okay, whatever the tree itself is predicting. Okay. Actually, did you just say regression random forest classification? It doesn't really classification or regression. M is equal to B. Oh, sorry. M is equal to P. Yeah. You're just aggregating trees, right? So yeah, it's the same thing. Yeah. Good observation. Okay, so basically this averaging formula makes sense for regression, and if you have classification, you have to take a majority, right? Each tree will suggest a particular class, and then you can't just average classes. You have to pick the one which is the mode of the, like the most trees are suggesting certain class, then that's your prediction, right? I don't want to write that formula, but minor changes for classification. Okay, and so I think we saw a particular trick with not bagging, but bootstrap few lectures ago, and that was we could use and before, I guess we said we could use bootstrap for estimating test error or generalization error or EP, whatever it is, right? And so specifically for random forest or bagging, they have bootstrap samples, so we can also do the same. And in fact, I'm just going to recap what we suggested before. So before we said to get an estimate for test error, look at every example. Let's say xi, yi. Just look at which bootstrap samples this observation does not fall into, in a sense it's not a part of that bootstrap sample, and then pick up all those guys. So f hat star v's, which are the prediction models built using bootstrap samples which don't involve this particular observation, and then you evaluate the performance over some loss over yi comma something like this. Or if you're actually doing aggregation, you can get the aggregate as well, okay, the summation as well. So this is what was I guess it's called this is what we were doing before, and here, because okay, actually let me just write it separately. Okay, explicitly I'm writing that all those B indices where xi yi is not a part of that sample. Okay, a summation, I guess there is also a normalization. I'm not writing that, but this is called out of bag estimate. Okay, this you can do for every observation, right? And so you can do this for whether you're using bagging or whether you're using random forest. You can do the same, and you can do this for any situation where you're actually using bootstrap technique. Okay, so even if you're doing linear regression and doing bootstrap, for some reason, although linear regression will give you the confidence intervals, but if you care about confidence bands, you are anyway doing bootstrap. You can compute out of bag estimates even with linear models. Okay, any other model as well. Okay, and so these can be used instead of k-fold cross validation. Okay, but I think there will always be some caveat, some thinking you need to do if you're going to use this, depending on the bootstrap size and if you are overestimating or underestimating the test error. So ideally, if you want to use this method, you want to kind of convince yourself that maybe the expectation of this is actually equal to the test error. Okay, but since we have not shown that here, I will not recommend this as the method. So we try to use k-fold cross validation. And so in the note, I have an example of comparing this with gradient boosted trees. So how many of you could understand gradient boosted trees from last time? So the gradient boosting, okay, let me just quickly recap that. I mean, because it's an important concept, and I don't know, have you seen gradient boosted trees in the other course? You have? Okay. So So AdaBoost can work with trees, but I'm talking about gradient boosting, which is more general, right? That was the key point of last lecture. But okay. So just a quick recap so that you kind of put things in perspective. So gradient boosting methods try to just to put things in context, so AdaBoost had some weird algorithm. So the way that we introduced the AdaBoost method was we didn't write an optimization problem. We just said, okay, in AdaBoost we'll have a data set. We'll first build a model, and then wherever the model is making an error, we're gonna kind of bump up the weights of those observations, and then build another model and keep doing it. Okay, it was some greedy, some sequential procedure, but we didn't really write down a optimization problem, and then once we wrote that sequential procedure for AdaBoost, we said that AdaBoost is actually optimizing for exponential loss. Okay, where we define exponential loss to be e to the power minus y times f of x. Okay, for the two class classification setting where y takes a value plus or minus 1. Okay, and AdaBoost also had this inner step where it said get a good weak classifier. Okay, where we didn't specify what loss function it's optimizing for. We said there is a step where you're trying to add a new weak learner, right? A new model, and we said just learn a new model on this new data with new weighted data. Okay, we didn't really specify what was the technique there. Okay, so it was not exactly optimizing exponential loss. It's an approximation. It's just to understand, kind of get an idea of what is it optimizing for. Okay, AdaBoost. And so the intermediate step could have been trees, right? So if the intermediate step is trees, so you know how to build a tree. So you know the g of m in the mth step of AdaBoost. G of m, if it is a tree, whatever the parameters of the tree. So you'll build a tree based on trees criteria, right? Some maybe least square loss. You'll recursively greedily partition your regions and build a tree. Okay, but that has nothing to do with this. This exponential loss is a loss for the sum of these trees. Okay, the trees themselves you're building using a recursive procedure which has its own objective function roughly. Okay, so there's two levels here. There's a level at which you're asking for a loss function for the sum of models. So AdaBoost eventually will give you a sum of models, right? So it will give you sum over gm, m is equal to 1 to capital M, and I guess I don't remember what coefficients it was, maybe beta m. Okay, so this was the model, right? F at F. So it was a sum of a bunch of weak models, right? So for this level, we are saying the loss is exponential loss, okay, a particular loss. But while constructing GM itself, if you're using a tree, then it will have its own loss function, right? It will have, for example, Gini index based recursive partitioning, right? Okay, that has nothing to do with the exponential loss. You're asking for the sum of models, okay?
Why are we worried about exponential loss? Is it because of the penalizing example?
No, it's just a choice of a loss. You can have different losses for classification, right? You can have the 0-1 loss if it's just you can have 0-1 loss even if there are k classes. You know this cross entropy loss, right? So exponential loss is just one choice for a two class setting. Okay. No, so I guess the narrative is AdaBoost is doing this, right? AdaBoost is creating a sum of bunch of models, okay? So when you look at sum of bunch of models, there has to be a loss function, right? So there has to be an L which corresponds to yi and this f hat of xi, where f hat of xi happens to be a sum of bunch of models. And each individual model by itself, how you're building, using its own loss function, like Gini index or something, okay? And so there has to be a notion of loss to kind of, for example, determine these coefficients, right? These coefficients which are not related to each individual model, but coefficients for the summing of these models. So for that, there is a loss function which happens to be exponential to kind of understand AdaBoost. Okay, AdaBoost is a technique set in stone, as in somebody has already described a sequential procedure for it, and we are trying to interpret that as, okay, in terms of summing up these models and computing coefficients, it's actually minimizing exponential loss. Okay, but now you want to move away from exponential loss, just as we pointed out. Why choose exponential loss? I can choose L to be, I don't know what. Okay, so let's say the cross entropy loss, or if it's a regression setting, maybe the Hoover loss. This is just examples. Okay, I can change the loss functions with which I evaluate the sum of models. Right. This is the sum of models setting, where in each individual model itself could be still a regression tree, and that would, if it's a regression tree, then I would use, let's say, squared loss. There's a bunch of choices there also, but there's a choice of loss function even at the aggregation of models also, right? And so if you change the loss from exponential to something else, let's say Hoover loss in the regression setting, or the classification setting, then there is no corresponding AdaBoost. Okay, there is no reweighing of weights that you can do. Okay, there is no AdaBoost anymore. So we have to define another algorithm that that creates this thing, which is BM GM of X. Okay. We need to have another algorithm which creates this, and for that we said let's try to mimic one aspect of AdaBoost, which is AdaBoost is adding one weak learner at a time. Okay, so we'll also try to add one model at a time. Okay, and so that's where we said there is something called forward additive stage-wise modeling, I guess. And all this just is saying that I want to add one model sequentially, one at a time. And to do so, one way to add a new model, if you're trying to consider what new model to add, right? So figuring out what should be GM. So you already have G1 to GM minus 1 in your bucket. You've already chosen these models, let's say, somehow. And you're asking, how do I add GM? Okay. Then you have to kind of look at the loss, actually. Okay. So you have to look at the loss and somehow add, I guess, let me write, look loss and figure out the next best, I guess, GM. Okay, and gradient boosting method does this. Okay, using gradients of the loss. That's all. So we need to figure out how to add a new model. For any loss, we just need to look at gradients of that loss. Okay, but there is a incompatibility in terms of, okay, I can look at the gradients of the loss, but with respect to what? What are the parameters? Should I look at the parameters of GM itself? So think of GM as a tree. I want to add one new tree. The mth choice of a model will be a new tree. But the tree will have its own parameters, right? The parameters of a tree, generically speaking, are going to be the regions and the constants of those regions, right? Roughly, those are the parameters of the tree. Okay. How can you take gradients with respect to the regions and the parameters of and the constants in the trees? To kind of avoid that, what they do is just they take the gradient with respect to every observation. Okay. So you get a n-dimensional gradient. Okay. So don't take the gradient with respect to the tree's parameters. Take the gradient with respect to the current. Think of so if you have a new model, the model will be evaluated at n points, and those points would be added to compute your empirical loss, right? So your training loss, this L, is actually just going to use the model at n points, n observations, x1 to xn, and then those are the numbers which will form to kind of compute your loss, right? I don't know if everybody followed that. All I'm saying is, even if you had a model, let's say hypothetically, I somehow chose a model. The model is just evaluated, right? So it's GM of x1 to GM of xn, and then these are the numbers which kind of are plugged into your loss function, right? Roughly, I mean that's what's happening. Even if you had a full description of the model, only n numbers are used to kind of get a new loss estimate. So gradient boosting method, all it's saying is, first just think of these n numbers as variables, okay, as in they're not fixed. Think of these n numbers themselves as parameters, basically, as in not fixed. Okay, take the gradient of this loss with respect to those n numbers, okay, at the current point, okay, so that you'll get n gradient values, okay, and then you fit, let's call that n-dimensional gradient GM, okay, little gm, I guess we'll put a vector there. Then fit GM and xi, whatever these are, I is equal to 1 to n, using a tree. Okay. So they're decoupling the problem in the sense that first they're computing the gradients, which are n numbers, and then using those n numbers as labels or as targets for the tree building process. Okay. So the tree, when you build a tree, you're not using the yi's, which are the original data. You're just using the gradients as the targets for your tree building. Okay, that's it. So that's what a gradient boosting method is for trees, for example. Okay. Any questions here?
How do you calculate the
Take the gradient. Take the first derivative of the loss. So loss is a function of these n numbers, right? So for example, so square loss, for example, right? So you have yi minus, let's say previous all models are fixed, so there will be some over plus, let me call this zi, okay, square, okay, sum over I is equal to 1 to n. So let's say this is the square loss. I'm just taking some loss, right? All I said is, let's ignore maybe there's a beta m here, okay, somehow. All I'm saying is, you just want to find the gradient of this with respect to d by zi for all I is equal to 1 to n. Okay, you can find this gradient and evaluate it at the so evaluate it at the current value. So this is the evaluate it at current xi basically. So if it's a function of zi, okay, wait. So let's say we take the derivative. It's just 2 times minus the whole thing, whatever this is, so whatever constant, plus zi, right? So I guess there's a detail in the note I'm not recollecting now. So it just tells you what zi you need to substitute there. Okay. So you'll get a number here basically, some other constant c2. Some other constant. Okay. So that's it. So I don't recollect exactly what zi you need to plug in there, but I've written that in the notes from last time. Which if I had, I will just show it to you, but maybe in the break I'll just check. Yeah, so you just compute these n numbers and then use these n numbers as targets for your tree building, for example. That's it. So that's gradient boosting machines for you. And they have really good performance. I think in this note, in this note, there is a small example in the note itself where we are showing the performance of random forests with choices of m. So I don't know what the actual number of input variable dimension was. The p I'm not sure, but there was a choice of m, which is, for example, here 2 and 6, and the gradient boosting method with trees. So if there are trees, then you can choose the depth of the tree. You can terminate your tree building procedure when the number of when the depth of the tree is 4, for example, or the depth of the tree is 6. Okay, and they're just showing the test performance actually measured in terms of absolute error. So it's not really over your training data. Once you have already built with some appropriate parameters, for example, the number of trees in random forest and the number of I guess weak learners or number of models in your additive model in gradient boosted machine, they're all fixed, and I don't know what those numbers are, but once you do that, you're just evaluating over actually it's a function of trees actually. Okay, so they're actually plotted as a function of tree. As you add more and more trees, what happens to the test error. Okay, I mean, this is not something you get as a diagnostic when you're actually building your model, but this is something you can.
The gradient boosted trees on average reduce the variance error more than random forests because they tend to outperform in reducing the variance error.
Do they tend to reduce the variance? What do you mean by that?
No, so random forest is supposed to reduce the
variance
error, right?
Yeah.
Is the gradient boosted trees doing that better usually, or is it just, I don't know if it tends to perform better?
So they're adding different trees, right? So it does tend to perform better, but that's because both are essentially sums of trees, right? Eventually, whether you use gradients as targets and build trees, and so those are potentially different looking trees, but eventually your prediction is just going to be a sum of all these trees, okay, for both random forest and gradient boosted machines. So it's just the characteristics of the trees are different, which lead to better performance. It's not strictly about variance. So the variance comparison was only to understand between bagging and random forest, right? Bagging was taking all the input variables, and random forest was selecting m as random, m as a subsample among these p dimensions. So the variance intuition makes sense for bagging and random forest, but not for these two, because they are not even they are not similar at all.
Okay, would you say it tends to perform better than random forest though? You can do something like
Yeah, empirically. So I would say that given this class, you should, the holy grail answer is that there is a joint distribution between input and output, and we don't know which one is approximating the conditional expectation. We don't know. I mean, it doesn't have to be right. If the conditional expectation is actually just linear, then a linear model is always going to be the right answer. You don't have to do all this, okay? But you don't know what what the intrinsic conditional expectation of y given x, for example, is. So empirically, you will have to try and look at cross-validation scores or proxies of these test error scores. And yeah, I think in practice it looks like GBM performs better, but doesn't mean that it will perform in your data set in the future. Yeah.
So it goes down as you increase the number of trees. So does it mean that if you become added
In this data set, it seems to be decreasing. Yeah, the test error. Yeah, doesn't have to decrease. I mean, it's not that far. It's still 0.32. Maybe it's plateauing here. I don't know.
So it's very good, I think. So AdaBoost tends to overfit if you have too many trees, right? Does that apply to you?
The overfitting is you're saying there is going to be an upward curve here.
Right.
I have not demonstrated it.
But does that apply to gradient boosting as well as it does to AdaBoost, or is it different?
It may, but in this, at least, this is a function of. So you're saying if I add more trees, I can potentially expect a upward tick. Yeah, it's plausible. It's very plausible because more trees means more degrees of freedom, right? So you have every individual model has its own bunch of parameters. You have you're adding every time you add one additional submodel, this GM, in AdaBoost or random forest or gradient boosted methods. You're having more degrees of freedom to fit your data. So of course your training error will decrease, and since you're using more parameters, you could potentially overfit, and therefore your test error could go up. Right. It doesn't, as in there is a theoretical result which says it will never overfit. I don't know. See, empirical statements, I'm not sure what to make of them. But just think of it this way. Maybe, I think one way, so people have tried to understand the overfitting behavior of AdaBoost for a decade or whatever, 2 decades now, since its inception. There is a camp which says it doesn't overfit because it does some implicit regularization. But I'm not aware of those details. Okay. But I don't know. It would be great if you can tell in the next class what's the detail. Yeah.
So since AdaBoost also works as that, we have a bunch of group members which don't do the same use case. So does gradient, it works better AdaBoost back up. They are not doing the same use case.
Yeah.
Does gradient engineering also works as that should have a bunch of same set of use case?
It's about you have a loss function surface and you want to go down the surface. So you take a gradient step, a negative gradient step along that surface, basically. And so it's like a gradient method, except that those gradients are being used to build the next model. So it's really an optimization point of view rather than making mistakes on same observations again and again. That's not the right view here. At least there is no simple way to kind of understand what's happening with gradient boosted machines other than the view I just presented. Is just you have a loss function, arbitrary loss function. You want to take a gradient with respect to that. Take gradients first and then map the gradients back to whatever model you're building. Basically, that's the idea. It's a very straightforward idea, actually.
Can we be sure that we're always gonna get to the overall optimal, or can we get stuck in a local minimum of the gradient?
If the loss function is convex, for example, and you're doing gradient descent, then you'll get to global optima. Appropriate choices of what are called step sizes, you will get to global optima. And if the loss function is non-convex, as in it's all it has hills and valleys, then gradient methods will not get you to global optima. Okay, so let's take a break for 10 minutes and resume.
different office hours besides the Friday from 5 to 7? Or no?
There's also Thursday 5 to 7 as well. So we have two
Thursday?
TAs. We have two TAs. So each one is Thursday. I don't remember the exact. Let's see.
Because I want to talk to you the project. So
With me
that's-
you can just set an appointment and.
Yeah, that's what I'm saying. So I just don't want you to just come to school for me. You know what I'm saying?
No,
I try
I'll
to
be
catch
here.
you as well.
I am here through all the days of the week.
Okay.
Except
So
just next week I'm traveling.
okay.
Just next till Thursday I'm traveling.
Next Thursday you traveling?
No, Monday, Tuesday, Wednesday, Thursday, 4 days I'm traveling.
Okay.
But in general, all days I'm here.
Oh, okay.
So you can set an appointment and I can give you
Okay.
slots
Yeah.
any day of the week whenever you're here.
Yeah, because I have class on Tuesday and Wednesday at 6 o'clock. But
Okay.
I get out of work at 4, so I
Okay.
get like 2 hours. So
Yeah,
that's
yeah.
why I can catch you on
Yeah.
Tuesday and
So
Wednesday.
Tuesday and Wednesday would work, but not next week.
Not that quick. Okay, the week after is fine.
Yeah.
Okay, all right, thank you.
Yeah, just shoot me an email and I can set you a slot exactly and I'll be there.
All right, thank you.
Yeah. Yeah.
How many outlets on your
There is one. There is one here. Yeah, there is one.
Oh, is it only one?
No, there is two.
Okay.
Yeah,
Thank
can find
you. I realized I couldn't reach that one
it.
there.
Okay.
Thank you.
Probably the first thing that we check about weighting boosting, but then, like you said, at a single point for a model GM, at a single point we'll get n gradients, right?
No, so GM comes a bit later. You just think of actually I have the notes from last time. So think of bring in the GM later, but think of I have a loss function like this. So FM has to have these m. FM is just the sum of these GMs. Okay?
Right.
G1 to G,
Right.
G1 to GM.
Yeah.
So first you just think of these FMs as n different numbers, which are you're not thinking of a model anymore. You're just thinking I have m numbers. I want to kind of differentiate this with respect to these m numbers because these are now symbols or basically parameters.
Oh, so we're differentiating L in
L with respect to this.
Okay.
And see, this FM is evaluated at x1 to xn.
Right.
So there are
Where
n
is the
evaluations.
size of the bootstrap sample, right?
N is just a number of observations, not bootstrap. Don't even confuse with bootstrap. You
Oh,
just have
sorry.
data with n observations. So n is the see. Anytime you have a model on training data, you only evaluate at n points.
Endpoints.
So think of those n numbers. If you evaluate on n points, you get n numbers, right?
Right.
Think of those n numbers now as variables.
Okay.
So you can always take the derivative of this function with respect to
With
those n
respect to
numbers.
n numbers,
Yeah.
okay.
And that's it. So that derivative happens to be, it's basically derivative of L, with
Right.
respect to.
With the-
I mean,
all the numbers.
I could have just written f of xi to be some zi or something, and so
Right,
it's just a
right.
derivative with respect to that.
Okay.
And then if something like this would happen, the zi would still be there if I take a derivative. You just substitute a zi to be equal to the previous, when you haven't. So basically, substitute this number here. Because this is an additive model, right? Where is the, basically substitute zi equal to just sum over j is equal to 1 to m minus 1 of gm of xi. Actually, maybe there's a beta m. I don't know. Yeah, these are all known. So because you have already chosen these m minus 1 guys. Oh, sorry, I should write j. Okay, this is summation over j. Sorry, m minus 1 such models. So so this will be one number, some constant, and then you get n such numbers because they take a derivative with respect to every zi. I is equal to 1 to n.
Right.
So I have n numbers. Now you ignore this loss gradient business.
Yeah.
I have n numbers.
So I have
think of
gradients.
those n numbers and your features as your new data. Fit a tree,
Okay.
and then you come back with a tree. That tree will be your GM.
So n number doesn't with respect to every gradient, I have like.
Yeah, every gradient would give you one constant. Gradient with respect to every observation.
Right.
Essentially, observation index would give you one number. So you have this gradient with respect to 1, gradient with respect to n, and the usual xi's would always be there, right? x1 to xn. So just think of this is your new data and fit a tree. Yeah, that's just called gradient distribution. Boosting because it has some relations to boosting, that's why. But gradients because it uses
ultimately we are coming down in the.
Yeah. So the tree part only comes once you get the gradients. Now you forget about the main problem, fit a tree, and once you come back to the main problem, in the main problem because you're taking gradients and taking the. Actually, I think you're supposed to take the negative gradients. Okay, I mean you fit the gradients and then take the negative step or something. In the original problem, if you have a loss function something like this, if you're at this point, take a negative gradient and keep moving down. Yeah. So the right picture actually is gradients are not in the. So if you think of L and X, so this is the X point here. Gradients are negative gradient just means go this way. Okay? Because gradients are supposed to be in the X space, not in the. Pictorially, all you're saying is it's like a tangent and you're going this way.
But on the x-axis.
You're basically moving this way. So this is the lowest point. If it's a nice function, you keep going towards this way.
Okay. But then again, you mentioned if they're like hills and valleys, it won't work.
Yeah, if it's arbitrary like this, then you will get stuck here, right? You will not go. You will negative gradient.
There are global minima and local minima.
This is called a local minima.
Local minima. There's a global minima, so it won't like go to the global minima.
No, global minimization is hard.
Just
So you can see that whether you're on this side or this side, negative gradients will only go to the local minima. Yeah, so you'll never kind of go out of this and come to maybe this is the global minima. It will never go here. Okay, so let's resume actually. So we're going to look at a couple of things which you've already probably seen in the other class, which is going to be variable importance plot and partial dependence plot. Okay, it's just a couple of quick concepts trying to understand what random forest does. Okay, let's. So the first one is called variable importance. Okay. I mean, actually, maybe the partial dependence is not specific to random forest anyway. So I'm going to just explain what these two are. In fact, if you fit a random forest method or a model to your data, people will expect to see this, a variable importance plot. Okay. And it's something that you can also build for random forests and in general tree-based methods. Okay. Bagging, tree-based methods like cart. Okay. And basically the idea here is to figure out which input variables are very important or most relevant for the prediction task. Okay, that's the idea. You just want to know, out of your p variables, can you order them in some way such that maybe x10 is the most important for your prediction, maybe followed by x8, followed by x13 or something like that. So you're just trying to figure out an ordering between your input variables, 1 to p. Okay. and the way it's denoted for, let's say I'm looking at a variable L, okay, and I want to know its importance, okay. Let's say focus on the Lth variable, and we want to know its importance, and I'm just going to give you a formula for the importance, which is going to be, it will have too many superscripts and subscripts, but let's say L anyway, Lth variable for the tree T, okay. There's a square because it's a squared measure, okay, which is going to be equal to sum over little t is equal to 1 to j minus 1. So what is little t indexing? It's going to index nodes, okay. If you have a tree with j terminal nodes, it will have j minus 1 internal nodes, okay. That's a fact. So if a tree has 10 terminal nodes, then it will have 9 internal nodes. So that's why the summation. So we are just summing over every internal node, and we are saying what is the, we're summing over all internal nodes and saying, okay, did we use, so the variable used is L or not, basically. So I've just put it's like an indicator function. I'm just asking whether at this internal node did I use the Lth variable as a split choice or not, okay? Because I don't care if L was not used for the split choice, then it was not used at all, so there is no need to account for it. So just indicator of variable use is L, and then I'm just gonna have something called I hat square at that split T, okay. So what is I hat square? I hat square is just going to be the difference. So think of so I'll just illustrate it here. So at any split, there's an original region R0, and you're splitting it into R1 and R2, right? At any split point, it doesn't have to be at the root of the tree. Any node, you're splitting it into two parts. You'll just have two regions. And the way, when you split, before the split there would be a constant on this, which would be C0, and after split there would be a constant which is C1 and C2, right? That's the whole recursive procedure for tree building. And so let's say this is the node little t. Then all I'm asking is, what is the improvement, okay? So I hat t square is the relative improvement, okay? And what does improvement mean? Just think of it as, for example, when I split, I'll have a particular for example, total squared error, right? For example, let me write it for squared loss. It would be yi minus c1 square sum over region 1 plus sum over region 2 of yi minus c2 square minus sum over region 0 of yi minus c0 square. So of course, where I is such that I belongs to that region, when I say sum over region, this is what I mean. I is such that xi belongs to that region, actually. Okay. I is such that xi belongs to that region R1. So this is a relative improvement, right? You kind of broke down the region into two parts, so you kind of reduce the error, mean square error, for example. Squared error, for example. Okay. So this is it. So once you can compute this for fix a variable, figure out which all nodes it was used as a split variable, just compute these improvements, add them up. That's your importance for this variable this variable L. Okay. And you can compute this for every variable 1 to p. Okay. And then you can sort them in order. Okay. Compute for L is equal to 1 to p. Sort them in order and scale the largest one, the largest scale, the one with the largest, I guess, I. And the last step is just scaling, because these improvements are all relative, so there is really no absolute numbers here. So you can scale the largest one to 100 and then scale everything else accordingly. Okay, it's like a multiplier that you're multiplying with for all of them. So an example plot is I think here, yeah. This is for relative importance of certain variables in some prediction task. So you just scale one of the so it just whatever was the capital I square for this med inc, you just scale it to 100 and you scale everything else, and this is how you get a variable importance plot. Okay, any questions? Yeah.
What if we have like relative correlating variables and if will the correlating variables come at the top, like for let's say there's a variable in the labeled to variable A, will both the variables come as at the top as important variables or just one?
Two correlated variables. No, it will have the same issues with collinearity as you would see in linear regression. So the presence of one variable may kill the effect of the other one. So here I cannot say that if two are correlated and both are important, if both will be at the top, I cannot say that. I don't know. You can further investigate and tell me the answer.
So do we have to ensure that they are not present
No, in the random forest, at least it's kind of decorrelating things, right? It's only selecting subset of these input variables as a split choice. So hopefully it will capture, if both two correlated variables are both important for predicting something, maybe both will be captured in this importance plot. Okay, so the partial dependence plot, so next one is a technique not specific to random forests. Okay, it's just trying to understand. Okay, I have a f of I have a predictor f of x, f hat of x, and I want to know how does it depend on just let's say variable x1 and x2 only. Okay, I have maybe x1 to xp. I don't want to understand what is the dependence with respect to how does my prediction depend on x1 and x2. This is what I want to understand. So and the way to do this is very straightforward. You can construct this function called I guess partial dependence function. So let me call this xs and I'll call this xc. Okay. Basically, xs is the set of things that we care about, whose over which we want to know the dependence or the variation of my prediction function, and complement of that is xc. Okay, and so I only want to know a derived function which only depends on the variables I care about. Okay, and so to do that, I'll just take an average over I is equal to 1 to n, my n observation data, right, of f hat over I'll ignore the x1 and x2 for example for my each I, and then I'll only take x I c. Okay, so remember xi, little xi was little xi1, little xi2 to little xip, right? I'm saying I'm gonna take the actual values that it took in the summation, those are these guys, and not use the values of the first two coordinates, for example, because they are in my xs. So I can evaluate this, I can evaluate this for every xs, for every xs I can find this function, right? Let's say x1 and x2 vary from 0 to 1. So for every pair of values, let's say I break them into grid points. So for 0, 0, I want to kind of find the summation. Okay, I'll fix xs to be 0, 0, find the summation. I'll fix xs to be 0, 0.2, find the summation. I'll fix xs to be 0, 0.4, find the summation. Similarly, I can explore the whole grid, right? Okay, so this is called a partial dependence function, and this is how. So then you will just plot as a function of maybe x1 and x2. How does the 3D surface look like? Okay, that will tell you as you vary x1 and x2, how does your function, prediction function vary. Okay, you're basically cancelling out the effect of all the other variables by averaging. That's the that's the key idea here. Okay, let's look at the next method, which is called multivariate adaptive regression splines. Okay. And we'll also try to understand the nomenclature here. Multivariate just means, multidimensional data. So that's easy. Adaptive means we're gonna do something similar to what we saw with AdaBoost and gradient boosted method. We're gonna add one new object at a time. Okay, so adaptive just means sequential here. Regression, because we are focusing on regression problem here. And splines are just, I guess, names for some classical objects. These are just functions. Think of them as functions. Okay. So adaptive just means we are going to do something sequentially. Okay. And the reason why we're introducing this particular method is to kind of get an idea of more complex, more nonlinear regression functions, regression models. Okay. And in particular, we're gonna try to build a model which will be like this. So it's gonna be f of x. I'll use capital X, as this beta naught plus sum over m is equal to 1 to capital M of beta m times, let's call this h tilde m of x. Okay. So I'm thinking of building a model which is again gonna look like this, which is basically a sum of bunch of other functions, and I'm going to define what other functions are. But to define these functions, let me first. So these functions will be functions that I'm going to describe in terms of another set of functions. So let me first define the simple set of functions first, and those are called. So those are these functions which I'll write right here, x minus t plus, okay, and t minus x plus. So think of one-dimensional function actually, one-dimensional function. I guess one-dimensional input and one-dimensional output. Okay, so and this is a function. Okay, it looks very weird. I'm just going to draw it because it's just a one-dimensional thing. Okay, it's going to be this. So t is a parameter of this function, and x is so x is the variable. So this is basically, let me call it h of x. Okay, so it has one input. Okay, it's going to be one dimensional. It has a parameter t, and how does it look like? So it's going to look like this. On the x-axis is the one-dimensional variable x, and y-axis is the evaluation of the function. Okay, and let's say there is a point t, because t is again some number. So let me put the point t there. And so it's saying when x is less than t, I'm gonna make the function value 0. Okay, and when x is greater than t, I'm gonna consider x minus t to be the function value. Okay. This is the function, which is x minus t plus. Okay. It's just a definition of a function which is like flat on one side and rises with a slope of 45 degrees on the other side. Okay. And t minus x is just the opposite. It's gonna, maybe it's another function h, let's call it h1, h2 of x. It's just gonna be going up this way and then flattening out here. Okay. At the same t. Okay, with these types of functions, so now I'm going to kind of define these functions over my data set. So now let me bring my data sets in, which is this X matrix. Let me just care about the input variable observations for now. So this X, if you remember, was x1 to xn, right? This is the n cross p matrix, right? I guess transpose here, because they are now row vectors. In fact, let me write it explicitly. It's going to be x11, x12, x1p to xn1, xnp. Right? That was that matrix, data matrix. Now I'm going to define functions based on this data matrix as this. Substitute every t with xij. Okay, where I is the ith observation, j is the jth variable. Okay. Set t is equal to this, then you'll get one function, right? H of, I guess I don't know if I indexed anything like that. So you'll get some h of x, right? According to that appropriate t that you chose. Okay. So how many functions do we get? N times p functions, right? Let's call this set of functions, C. Let's call this set of functions C. So far I've just defined some bunch of functions, okay, based on data. They're just one-dimensional functions. But now I'm going to try to come back to my original story, which was to build this additive model, okay, I guess adaptive model, because I'm going to add one function at a time, one h tilde function at a time. But these h tilde functions are not going to be the functions I just described. They are going to be some an additional twist to the function that I described, okay. So what is that? So how do I now build my Mars model, okay? So it's going to be again sequential. So maybe I should motivate with an example directly. Let's start with so remember, so Mars model was I guess is f hat of x is beta naught plus sum over h tilde of x. I guess there was a subscript. M sum over beta m is equal to 1 to capital M, right? So this was the Mars model, and so I'm going to add one function at a time. So I'm going to do first thing, step 1. I'm going to first find beta naught. Okay. And how am I going to find beta naught? I'm just going to okay, I'm going to first also choose the loss function to be squared loss. Okay. Okay. Squared loss, usual loss. This is the Mars model. Squared loss. Find beta naught by saying I want to minimize over beta naught of sum over I is equal to 1 to n yi minus beta naught square. Okay. This is very simple, right? I mean, I'm just asking for a constant such that the constant is the sum of the square values here is the lowest. Okay, and in fact you know what the closed form expression for this is, but let's not worry about that. You found beta naught. Next is the interesting step, which is consider NP functions of the following form, okay, which is going to be beta 1 times 1 times xj minus t plus beta 2 times 1 times t minus xj plus. Okay. So there are NP such functions, right? NP such functions for each t. So I can change t to be xij. Remember, I created such NP functions, NP number of such functions, right? So I can consider functions of this form. Okay, it's just going to be beta times something plus another beta times something. So for these functions, what is the only things that I can for these functions which are going to be still NP in number? What are the only things that I can set? The only things which I can set are beta 1 and beta 2, right? Only things which vary, which I can change now, right? So what I'm going to do is as follows. Now I'm going to, let's call this h tilde 1 of x, okay? Actually, let's not call this h tilde 1 of x. So what I'll try to do is minimize over beta naught, beta 1 and beta 2 of the same thing, like sum over n of yi minus beta naught minus, this term here square. Okay, I can do this for every, I can do this NP times. Okay, right? Because j is the variable, input variable. So remember, we created NP such functions, right? I just said think of this one-dimensional function x minus t. So t is a parameter of this function. So I said let me pick the parameter to be these NP values, n times p values, one of these n times p values. Then if I pick let's say x12, then I'm kind of focusing on the first. So I'm kind of focusing on the second input variable. So the variable part would be x2. Okay, so that's why I just wrote xj minus t. Okay, where j can vary from 1 to p, and if you fix a j, the t can vary from x1, x1j to all the way to xnj, like a column of that X matrix. Okay. So all I'm saying is you have NP. So if I write this type of function, it has beta 1 and beta 2 as coefficients, and there are NP such functions. I can plug in each one of them and optimize for betas. Okay, it's a lot of computation, but yeah.
So you're not optimizing for t, or how does t be determined then?
T is determined already, right? So all these NP points, NP numbers are going to be the values of the t. So there are NP such choices. So like I can pick t to be x11, then the function is going to be x1, capital X1 minus this x11 value that I observed in my data. So training data determines t by default, right? I said set t is equal to xij, and you'll get NP such functions, right? And since if you set t value, the only other value is x, I just said x to be the xj, the corresponding. If you take t to be xij, then the x itself is xj. Okay. All I'm saying is, plug in each one of these functions. Try to optimize for beta 1, beta 2, and beta naught again, and see which of these functions kind of fit your model, fit your data better. Okay. This is just the same residual sum of squares, except the functions are changing according to your choice of t, basically. If you choose t to be x11, then it's a function which only depends on the first input variable, okay, at this point. And if you choose t to be xnp, then it only depends on the pth variable and only the data point xnp. Okay, the t will be only xnp and xj would be xp. Okay. At this point, it seems a little bit, so why did I explicitly write down times 1? Okay, and I'm gonna do another step of this process to kind of give you an intuition of what's happening. Okay, so let's say you chose maybe out of these NP functions, the particular function which gave you the lowest sum of squares happens to be x72, which means that the seventh observation, second variable. Okay, in the sense that basically you could find a beta hat 1 times x2 minus little x 72 plus beta hat 2 of x2, I guess, little x 72 minus x2. You found this function to be the one which is minimizing my residual sum of squares. Okay. Let's say this is an example choice, and maybe this was the one which minimized the residual sum of squares. Then in the next step, so I'm gonna put this function in my set of functions. Okay, so I'm gonna now start collecting a set of functions. So I'm gonna put these two functions in my set of functions. Okay, so m is going to be I guess these two. I don't want to rewrite them. And I'll also use a constant function which is 1. Okay, so now I'm just writing down, just kind of keeping track of some function. So I just wrote, okay, let my set of functions let's say default, let's say have a constant function, and let it also have these functions that I chose according to my my one step procedure. And now I'm going to describe the second step procedure, and you'll see some pattern. Okay. So now we just added one, I guess two functions. I guess they are symmetric. So two functions we added in the set M. Now we're gonna try to add functions. I guess add see this set capital M is actually, I guess script M is actually capturing the terms of your Mars models. Remember, Mars model had the summation over little m of h tilde, right? So they said we are trying to build a model like this. And if you see here, we actually have beta naught and some beta 1 and beta 2. So we actually have three functions now, right? Two functions, which were this guy and this guy. So we added those two, and so that's why I'm just keeping track of the functions to be whatever this guy was and whatever this guy was. So we just have 3 functions now. 3, I'm just saying 3 because the first function, think of the first function as 1. So beta naught times 1. Okay. So I'm just trying to capture more and more functions in this set script m. And the size of the set script m has to be capital M, the number of terms in my Mars model. Okay. So now I'm going to add 2 more functions. So in Mars sequential model building, adaptive model building, it's the same name. I'll keep adding 2 functions at a time. Okay. And these functions just happen to be, are just derived from the basic, plus and x minus t function that I defined earlier. Okay. So let me add 2 more functions. So it's going to be as follows. So to add 2 more functions, these are my choices. In the first set, I had n times p choices and np choices, right? Those were all the potential functions I could have added. Every one I checked, and I added the one which had the lowest residual sum of squares. Now I'm gonna call what choices I have from the following. Add 2 more functions from the following choices. Which is going to be pick a function HL from this set script m, and pick HL from script m, and pick one of the x minus t plus or whatever or t minus x in the set C. Okay. So we define set C to be all these types of hinge type of functions actually. So pick one from here, pick one from there, and then you consider, so your choice is beta hat, let's say m plus 1 HL of x times x j minus t plus beta hat m plus 2 HL of x times t minus xj plus. Okay. So this is your choice. So for every function in my set, in my script m set, and for every function in my set of C, in the set C, I'm just gonna consider functions of this form, which is just products. Okay, they're just products. HL times one side of the hinge function and HL times the other side of the hinge function, just weighted by some constants. Okay, and now again I have these so many choices. I have actually choices which are like if m has 3 functions and C has 10 functions, then I have 30 choices, right? So for every all these 30 choices, I'm going to put it into residual sum of squares thing, which you just saw here. Okay, where is it? Yeah, so this one, instead of minimizing over beta naught, beta 1 and beta 2, I'll minimize over beta naught, beta 1, beta 2, and if it's the second step, beta 3 and beta 4. These are the choices that I have, and I'll pick the choice which minimizes the residual sum of squares. It's a little bit involved because I'm defining functions and I'm multiplying functions with each other, but the idea is to adaptively or sequentially add a bunch of more and more complex functions. Okay. Where the complexity is just that if the functions that you've already considered and the functions that you want to consider, the functions that you want to consider is always going to be the functions you've already considered times some base set of functions. Okay, the base set of functions are these x minus t plus and t minus x plus. These are the base set of functions. You've already considered a bunch of functions which are represented in script m. I'm going to always multiply them, and they will always create my choices for my next additions. Okay, in this way. And So you are now wondering, like, what is the point of having these hinge type of functions, right? Like, why does it help? So hinge type of functions are actually just capturing some nonlinearity, right? Think of linear functions. Hinge functions are capturing some nonlinearity with respect to each coordinate, each input variable. Okay, so that's how they are trying to at least capture some nonlinearity in your while trying to kind of approximate the conditional expectation of y given x, right? That's always the case. In linear models, conditional expectation of y given x was just linear function. But here we are just trying to approximate it using more complex functions, and some people figured out that this is a way to kind of gradually increase complexity by considering these nice one-dimensional nonlinear functions. Okay? So a function which looks like this is nonlinear. Okay, and we are considering all these bunch of nonlinear functions and constructing our predictive model this way, okay, sequentially. And yeah. And there is also an intuition about why you're multiplying functions. Okay, so for example, here multiplying HL with some function which is t minus, let's say for example, I'll give an example. If you see above, we chose x72, x2 minus x72 plus to be one of the functions, right? To be one of HL, one function in script n, right? In the first step, if you remember, we added this and we added the symmetric version of this as well. Now let's say in this step, these were the choices, and maybe when we looked at these choices and minimized for the residual sum of squares, it just happened that the particular t that reduced RSS was let's say x51. Okay, then basically one of my new HLs, then we add actually x2 minus x72 plus like one of the functions is going to be x5 minus not x5, x51, sorry, x1 minus x51 plus. So this is one function that we have added now into our basket of into our script m, right? Because t that reduced the residual sum of squares happened to be x51, the functions corresponding to x51, right? And maybe t that reduced the residual sum of squares, so x51 with HL being this guy, with HL being this guy. Okay, then you add this product into your set of script m functions. So what this product is actually trying to do is capture it's trying to capture certain parts of the input space. So think of this, right? If I have a function like this going up, okay, another function in a different dimension going up like this. So if you look at their product, it's like saying there is going to be a an upward slope somewhere over here. Basically, they're going to move away from. So there's going to be an upward slope here. In this region, there's going to be like a upward slope, right? Can you imagine? So just for these two functions, there are two hinge type of functions. Then there's going to be a common upward slope here, and everywhere else it's going to be 0. Okay, it's going to be flat. So they're trying to capture some aspects, some local neighborhoods of the input region where they think they're going to make the best prediction for the y. So they're basically trying to capture this hill type of or not hill, but these small regions of the input space where they're trying to be non-zero. So they're trying to be sparse, and that some small regions of the input space, if you multiply many of these hinge functions, only in some parts of the input space it's going to be like a product of linear functions, but everywhere else it's going to be zero. So just another intuition of what these products of functions look like. But the main game is just to kind of go away from linearity. Okay, this is an example of that, and empirically it's seen to be doing well for regression problems. So, any questions? Yeah.
So then, going back to step 2, we're looking to add 2 more functions, but we're going to be adding the product of those 2 functions.
Yeah. When H2, so I just added HL. I just said this and the corresponding symmetric one is now a part of script M. Then you will pick every HL and all your base functions multiply again. So you'll get 3 products next time potentially, one of the choices, right?
So can you scroll down?
Yeah.
So
if
that product of x2
Yeah.
minus x72 and x1
Yeah.
are you adding that to?
Yeah, we are adding that to M.
Okay.
And in the next step, you will consider this product and every function in C as one of your choices. So you'll have a 3 product next time potentially as a choice. I mean, that choice need not reduce your residual sum of squares. You may have a product, like for example, one of the HLs I said was just 1. So it could be just that one of the choices, which is just a single term, may minimize your residual sum of squares. Then that would be next HL to add into your basket. So you're incrementally adding functions into your basket, 2 at a time. Yeah, 2 because it's just symmetric, right? So you're considering both symmetric functions. Symmetric as in, like, if I consider xj minus t plus, then I'm also considering t minus xj plus together, while I'm trying to set these coefficients to minimize residual sum of squares. Okay, so my choice comes as like 2 at a time. So. Okay. So in the remaining 35 minutes, let's look at one of the more popular models called support vector machines. Okay. So how many of you have already seen support vector machines? And people not responding have seen it, but they don't want to say. How many of you have not seen it at all? Or it's not been taught in the other class yet? Okay. Okay, so use of the word machine, support vector, we'll kind of disambiguate that as well. Okay. And so support vector machine is an interesting new idea, and the reason we will kind of look at it today is to bring in this idea of kernels. Okay, so and we'll see what it does. So first, let's so we're gonna go back to the world of linear models. Okay, and then we'll try to say how can we extend from linear to nonlinear models. So Mars was a very messy way of going from linear to nonlinear models, but you'll see here that's a very nice way of going from linear models to nonlinear models. Okay, that's the fun part for this set of methods. So first we'll consider what is called a support vector classifier. And there's really not much of a difference. I mean, when people say support vector machines, they're thinking of kernel versions of them. We have not introduced that yet. So let's first think of a simple support vector classifier. What does a support vector mean in terms of this classifier? And then we'll get to the kernel stuff later. And in particular, we're just going to look at 2-class setup. Okay, we're only going to focus on 2-class classification problem. Okay, we're not looking at regression or anything else, even k-class version. And okay, I've used the notation yi as -1 and 1 to represent the 2-class labels. Okay, we were using G subscript I before for class notations. but I guess for this section, let's just use yi as the notation. Okay. And we'll also think of a hyperplane. A hyperplane is nothing but a linear function. Okay, it's just think of a hyperplane which is f of x is equal to beta transpose x plus beta naught is equal to 0. Okay, hyperplane is just x, all points x, such that they fall on the plane. Okay. So, for example, in 2 dimensions, hyperplane is just a line. Okay, for example, think of it this way. So, if I have x plus y is equal to 1, it will be a line like this. Okay, which will pass through 1 comma 0 and 0 comma 1. Okay, this is a hyperplane in 2 dimensions. Okay. And linear support vector classifier, or a support vector classifier, is just going to be a classifier based on this hyperplane. Okay, based on a hyperplane definition. Okay, it's just going to be the sign of f of x. Okay, so let me just motivate this. So what does sign of f of x mean? So think of the 2-dimensional example we had before, like oranges and blues, right? So we had what is it, right? Yeah, oranges and let's say blues, or whatever, these circles and pluses. Okay, we were considering a decision boundary. Yeah, okay, which we were hoping to be linear. In the initial few classes, we were considering, for example, LDA and logistic regression, and their decision boundaries are linear. Okay, so think of when decision boundaries are linear in high dimensions. So in 2 dimensions, it's the decision boundary being linear just represents a line, but in higher dimensions it's going to be a hyperplane. Okay, and the classifier is just going to be okay. So all the points here on the plane will be evaluating to 0, right? F of x for x on the plane is 0, so f of x is 0, and so all the points may be on one side, on the other side may evaluate to positive or negative values, right? So ideally, points on one side would evaluate to, let's say, positive. Then the sign of the evaluation would tell you which class it is. Okay, so let's say pluses are the plus ones actually, and instead of zeros, let me put minus ones here. Then let's say if the f of x is negative, then hopefully they correspond to minus, the negative class. Okay. So is the classifier clear? So I'm defining classifier as just saying I have a bunch of points. Okay, maybe they're overlapping or not. Here I've just separated them. Okay, that's not a big deal. So I first define a hyperplane which has parameters, which has, in fact, if x is in p dimensions, they have p plus 1 parameters here. Okay, because I'm explicitly writing an intercept, historical reason. Don't worry about it. So I have p plus 1 parameters here, and all I'm saying is I just want the on the hyperplane all points evaluate to 0. Towards one side of the hyperplane they will evaluate a positive number, and other side of the hyperplane they will evaluate a negative number. Okay, and so that's how I'm defining my classifier, just the sign of the hyperplane evaluation function. Okay, it's just a linear function actually. Okay, so now the question arises, which line should I pick? Okay, let's say this is the classifier that we want to kind of figure out, and by which hyperplane we pick is just a question of which betas do I choose, which beta and beta naught I need to pick, right? And for that we're gonna think in terms of what is called the margin. Okay, geometric margin. And margin is just going to be the distance of a point to the hyperplane of the classifier. Okay, so in 2 dimensions, let's say there's a point here and there's a point there. Okay, maybe 2 points here, all I want to know is this distance, okay, the perpendicular distance, okay. And let's say there are a bunch of other points here, bunch of other points here. Maybe these are the closest, and the margin is going to be determined by the closest point to this hyperplane. Okay. So this is called margin. And so the betas that I'm going to pick, I'm going to explicitly write down an optimization problem. It's going to, yeah. It's just a geometric intuition, right? You have a hyperplane, you have a bunch of positive points or positive class labels, positive class points on one side and negative class points on the other side. So I'm just saying find the distances of each point to the hyperplane and ignore all the guys which have high value. So think of only the closest ones. Okay. And in fact, think of the closest one. Okay. Maybe it's on the positive side or maybe on the negative side. So that distance of the closest point to this hyperplane, let me call that the margin. So there should be a confusion. Okay, what if the points are not, are overlapping? Okay, there's no distinction. There is no separation between pluses and minuses. They may be mixed together. We'll get to the mixed part just in a few moments. But if they were separated, I could define this geometric margin, right? All the distances of the points. Okay. And so to choose beta and beta naught, I'm going to define a particular optimization problem. It's going to look very different from, again, our conventional notion, right? We had a loss function and we were going to fit beta and beta naught. But here we are not going to think of it that way. We will try to fit a classifier and choose the betas, which kind of determine the hyperplane. We're going to fit the hyperplane's parameters, beta and beta naught, and also m, where m is going to be the margin, okay, right? Some constant factor times m. Pick that hyperplane, which kind of maximizes the margin, such that all points, okay, yi times xi transpose beta divided by norm of beta plus beta naught divided by norm of beta is greater than margin. Okay. Okay, so what have I written here? I'm just saying let's think of the positive class. Okay, y's are positive. Okay, let's only think about those points which are positive. Okay, yi is positive. Then all I'm saying is this number better be greater than the margin value m. So margin is this geometric number that I told you, right? The smallest distance of all points to this hyperplane. Okay. I just want this distance to be greater than so this number on the left hand side to be greater than that number for every point in my data set. Okay. So this number is going to be positive or negative depending on the sign of the points. So that's why I multiplied it with yi. Okay. The same intuition holds for the other side. So that's not the issue. So the issue is why this constraint. So why this inequality that I want to be satisfied for every data point is that if all data points satisfy this, then those data points will happen to be at least margin distance away from the hyperplane. Okay. All data points will be margin distance away from the hyperplane. Okay, so let me just write down the definition of distance of a point to a hyperplane. Okay, maybe that will give you some idea. So let's say there's a hyperplane here and there's a point here. Okay, so actually, so let's say this is. Okay, so this would be the margin. Actually, each point can have its own number, right? I mean, there will be one point which will be potentially the closest, but each point will have its own number. Let's say some number, let's say gamma, and so this is the distance of this point from this hyperplane. So there is a point here on the hyperplane. Let's call this point P. Okay, and let's say the normal to the hyperplane. So hyperplane parameter beta happens to be the normal to the hyperplane. Okay, so if a hyperplane in 2D space, like in a hyperplane in 2D is just this line, the normal to the hyperplane is going to be, I guess, in 2D, yeah, the normal is going to be 1, 1. Okay. So if you see, so x plus y is equal to 1 here, right? It was just 1 transpose, x, y is equal to 1, right? So the 1, this 1 vector is a vector like this, 1, 1. I mean, it doesn't have to be there. I mean, all I'm saying is a vector like that, right? Is this clear? So all I'm saying is, so let me write it explicitly. So this is 1 times x plus 1 times y is equal to 1. So I just wrote 1 times 1, sorry, 1, 1 and xy is equal to 1. So this would be the beta for this 2-dimensional example. All I'm saying is that beta direction is perpendicular to the line direction. Okay, and that's true for even higher dimension. So the distance of the some point x to the hyperplane is just going to be some multiple of okay, so so point P is going to be x minus gamma times beta by norm of beta. Okay, so just normalize the vector beta. Okay, multiply it with gamma. So that's the length of that vector. That's the length of this vector. Okay. Okay, and if I know this vector, I can write, think of it as a vector space, right? So I can write this vector and this vector in terms of that, right? It's just the sum of those two. So in particular, in fact, maybe I should put bars so that you remember what these vectors are. So P is just x minus that vector. Okay, so just a vector, simple vector equation. Okay, and but P satisfies, I guess, P satisfies P transpose, beta transpose x, beta transpose, I guess, P plus beta naught is equal to 0, right? P satisfies this equation, right? Because P belongs to the hyperplane, and hyperplane satisfies this equation. Any point on the hyperplane satisfies this equation. So you can do, you can just substitute the definition of P there. So it's beta transpose x okay, that I can write on the outside. So let me write gamma times the norm of beta plus beta naught. So this is the, so do you see I just substituted the definition of P here, and P has one part which is x. I just wrote the x here, and it had a negative part, so I wrote it on the right hand side. Okay, and the negative part is just beta transpose beta divided by the norm of beta. Beta transpose beta is the norm of beta square, so that's why one thing in the numerator just stays. Okay, and so this is the equation that x satisfies. Okay, x is not on the hyperplane, so I just substituted the point which is on the hyperplane, and we know if the point is on the hyperplane, this equation is true, and I just substituted the definition of that point in terms of x, and I just x satisfies this equation. Okay. Huh? Yeah. So this is the same as basically just bring down the norm of beta on here. So that is this thing here, and gamma is on the right hand side, and I'm saying the smallest gamma is my margin. So I'm just saying let all the points be at least that margin away. Okay, are you seeing the relation from here to there, or no? So which step is tripping you guys? So is this equation clear? So P is x minus gamma times beta divided by the norm of beta. Do you guys know what a norm of a vector is? No? So okay, so norm of vector in particular, I'm going to use this norm, is just the square root of beta 1 square plus beta 2 square, so on, beta p square. This is just the length of the vector. Okay. So basically, I don't know if you've done vector calculus or vector, I don't know what it's called, but so there is one. So this relation between the point on the plane, so you're just trying to find what is the relation between the point on the plane and the point out away from the plane, okay? And the point away from the plane is this x, little x, and point on the plane is this point p. And I'm just relating those two because I know that the normal to the plane is the beta vector itself. So this beta vector is normal to the plane, okay? If a hyperplane is defined using the beta vector, then the beta vector is going to be normal to that. Normal as in just perpendicular to that, okay? And if it is perpendicular to that, we only care about the distance, right? The margin is like a distance of a point to that plane. So beta is kind of capturing that direction, okay? So just normalize it. Normalize it just means that I think of a unit vector, which is just whatever beta is, just divided by its magnitude, okay? Its magnitude is this norm, which I just defined over here, okay? And just multiply with the length that I thought it was, gamma, right? So that would be that vector. And I have two other vectors which are p itself and x itself. So the vectors are related by this vector equation. Okay. So that this is just a vector relation between point p, point x. Okay. And then the next step, all I did was see point p also belongs to the hyperplane. So beta transpose p plus beta naught is actually equal to 0 because it belongs to the hyperplane. Okay. That is this step. Okay, and I guess the step which I skipped was just to substitute point p, which is beta transpose x minus gamma as a scalar, beta transpose beta divided by norm of beta 2 is equal to plus beta naught is equal to 0. I just substituted the definition of p in 1 to 2, right? I just did this. And I just split the, p has two parts, so beta transpose something minus beta transpose something, and this is a constant, so beta transpose something just happens to be beta transpose beta, and I said this thing, okay, beta transpose beta, if you have seen ridge regression, is just norm of beta square, okay, so norm you should have seen when you did ridge regression, okay, so basically the numerator is the square of the denominator, so you cancel one term. And you have basically this implies that beta transpose x plus beta naught is equal to gamma times something like this. Okay, I just put the negative term on the right hand side and left the other terms as it is. And if you divide now both sides by norm of beta 2, then you'll kind of left hand side resembles the term here. Okay. It's basically x transpose beta divided by norm of beta plus beta naught divided by a norm of beta. Okay, that's the left hand side, and the right hand side is gamma, which is actually the distance of the point to that plane. And I said I'm only concerned about all points to be at least m away. So I'm just asking for gamma to be greater than m. Okay, and why is there a multiplier yi? Because I want to take into account the positive side and the negative side. Okay, that's all. The smallest distance. So if there is a point which has a higher gamma, then gamma is greater than m, right? So then I can just put that m there. M corresponds to the closest point on either class. So if there is a, I think here I said x classes have some, maybe x is the closest point here, then I would, for the whole instance, that the distance of this x point would be the margin. On the other side, there may be another m, but take the smallest of those two. Okay, that would be my new m. Okay. So this is just a, so what I've done so far is just to try to kind of say, I can choose so many hyperplanes, let me choose the one with the largest margin, geometric margin, okay, distance from all these positive class and negative class. And I have only 12 minutes. Okay. So it turns out that the margin m depends on the scale of beta. Okay, because if I have a hyperplane with a hyperplane which is defined as x transpose 2 beta, okay, x transpose 2 beta plus 2 beta naught is equal to 0 is the same hyperplane, but I just multiplied beta by 2, right? Beta with 2, a scalar 2, beta and beta naught with scalar 2. The classifier will be the same in the sense, sine of this f of x is the same as sine of 2 times f of x, right? Because the 2 factor just kind of comes out, right? So there is a degree of scale issue with m. Okay, so I'm just going to choose the margin to be equal to and the reason is because I have not set beta to be this beta to be of any scale. So I can choose beta to be 100 times something or 1000 times something. I have a degree of freedom, and that's why the definition of margin also kind of becomes dependent on that beta. So I'm gonna set m to be equal to 1 by norm of beta. Okay, this is just to kind of kill 1 degree of freedom. Okay, either you say I only consider hyperplanes with betas to be exactly of unit length, that could be one choice, or you can say I don't want to constrain that, I want to just constrain my margin definition, which depends on the beta, to be just 1 by beta. Okay, that you can see, right? Why does margin depend on beta? Because gamma depends on the beta by norm of beta, right?
You couldn't just set a constraint on norm of beta.
Yes, you can.
Is equal to c.
Yeah, you can set norm of beta to be exact, like let's say 1 or 2 or something, and that would kill 1 degree of freedom. But we are just choosing m to be this. Is just for convenience. Okay. I mean, there's a out of choices that I could have made. I've made a particular choice this because it gives me a nice optimization problem. So the first optimization problem that I wrote, maximize the margins, seems as a geometric interpretation is there, but it doesn't correspond to our usual notion of loss functions and so on. So we'll get to that level. To get there, we are making some choices in between. Okay. So at least this should be clear, and we are saying that this has too many degrees of freedom because here I can multiply beta and then see if I multiply here in this equation beta by 2 times beta, so beta with 2 and beta naught with 2, then it basically means that I have 2 times the margin margin freedom, because even though maybe with beta 2 factor cancels here, but actually 2 factor also cancels here. Okay, this equation is independent of scaling. Okay. Yeah, I guess the reason is scaling doesn't affect the classification classifier at all. So if I have a hyperplane like this, or 2 times, if I have a hyperplane which has 2 times the parameters, it's the same hyperplane. So I want to kill that degree of freedom. So for that, I want to kind of choose the margin to be 1 by norm of beta. I mean, I can choose the margin to be some constant. I can just choose it to be 1 by beta. Okay. No, all I'm saying is there's this ambiguity of classifier choice, right? I mean, I can always scale the classifier and I'll get the same signs, right? So I want to kill that degree of freedom. So I'm just setting the margin to be constrained by that degree of freedom. 1 degree of freedom, 1 number. So I'm just relating the margin to the scale of the classifier. Okay.
But haven't we optimizing M? So if you're optimizing M, just figure it out.
Yeah, so the original optimization problem has too many degrees of freedom. So we are killing 1 degree of freedom by relating M to, so we are optimizing over M, beta and beta naught. We are just removing, we are just making M a function of beta. In particular, the function happens to be the norm of beta, so that we have a more constrained optimization. Okay.
Yeah, correct. Because you could have any values of M based on scaling you could have.
Yeah,
So we are shedding into one value which is
yeah,
norm of
yeah. Oh, yeah, I should say, I think in the previous reasoning I said 2 times beta. It's just a scaling of that normal vector that is the issue. That I can choose arbitrary normal vector. Okay, let me not go into that. Okay, I have less time. Okay, anyway, so let's choose this as the choice, and then we get a different optimization problem. Okay, we just substitute the value of M into the other setting, and there was a maximization over M. Okay. That changes to maximization over 1 by, I guess maximization of 2M. So that becomes maximization of 2 over something like this. Okay. I'm not writing the constraint, the inequality becomes this. Okay. And this we'll just say, okay, maximization over beta and beta naught of something like this is the same as minimizing over beta and beta naught of 1 by 2. Okay. In fact, we'll say this is the same as minimizing over beta and beta naught of 1 by 2 norm of beta square. Okay. I'm just making lots of reductions here. I'm just saying that maximizing, I just said we can substitute margin to be 1 by beta, 1 by norm of beta. So maximizing the margin is the same as maximizing this. This is a plain substitution. But here I'm making 2 additional, changes. I'm saying, okay, maximizing this inverted function is tough because beta is my thing which I need to optimize for. Let me flip the function and then minimize that. Okay, that's one change. In fact, I just don't like this function. Let me square it. Okay. So this is the second change. Okay. And these are, I guess, valid changes actually. If you square, so x square is a nice convex function. Okay, it's a monotonically, it's like a parabola, right? Yeah, x square is a parabola. Y is equal to x square is a parabola, right? So it doesn't actually change the optima, as in the minima of your optimization problem. So you can put a square; it's not an issue. Okay, unless I guess it's not an issue because the norm is also a positive function. It's a nice function. It's also a convex function. So what I'm saying is this trick here is fine. You can put a square as long as the underlying function is also nice. Okay, you can't just square. Let's say you had an optimization problem which was like minus 3 beta square or something. You can't just square it and they say, I don't have an issue with optimization. You can't do that. Here it's a legal move. Okay. So with this, this is pretty much the problem for support vector classifier, which is going to be min over beta and beta naught of 1 by 2 square of yi times xi transpose beta plus beta naught greater than 1. Okay, for I is equal to 1 to n. Okay, and it turns out that this optimization problem is a convex problem because this is just I just wrote down the definition of the norm, and if you square the norm, it's just the sum of squares. So this is a nice function, and these are just linear functions of the variables of this optimization. So it's a nice optimization problem. Okay. But I have not addressed the issue of overlapping instances. Like then margin doesn't make sense, because there's things on one side and things on the other side. So to kind of capture that, we are going to introduce something called slack variable. Okay, and that's going to give you, slack variable just means that, okay, for some data points I will not be able to meet the margin requirement, so I can't keep the data point. I can't find a hyperplane such that it is at least m away from the hyperplane. Maybe it's going to be m by 2 away. Maybe it's going to be on the other side. Although it's supposed to be a positive point, it's going to be on the other side. I'm going to kind of introduce something called slack variables, okay, to kind of account for that, and it's going to look like this. I'm going to minimize over beta naught, and ci. So there's going to be one slack variable per observation, okay. And what does that variable do? It's trying to capture the issue of some data points may not be margin m away from the hyperplane, and it's going to be like this: 1/2 of beta square plus c times sum over I is equal to 1 to n. So one slack variable per observation of ci, subject to same constraint there. So whatever that is, so yi times xi transpose beta plus beta naught is greater than equal to 1, and the constraint changes slightly to 1 minus ci, okay, and ci is greater than equal to 0. So basically we are saying, okay, if you are not able to meet the margin, which was that now changed to 1, if you can't do that, okay, maybe you can be greater than maybe 0.5, maybe ci is 0.5. So I'm willing to kind of get you closer to the margin. In fact, maybe I can make ci greater than 1, which means I'm willing to kind of put you on the other side, but my budget is limited. I don't want to kind of give ci bandwidth to every data point. So I want to penalize for for every data point if the data point starts to kind of consume this ci variable. Okay, so it's like a budget. So I want to try to minimize the aberrations, minimize the number of points which can kind of have a margin smaller than 1 unit now, because margin I just scaled it away. So anything which is less than 1, I'm going to kind of penalize for it consuming some, it's being less than that margin value. Okay, so this is the support vector classifier primal problem. And in the next class, we'll look at, why did we go through this, is to kind of get to, so that we are still in the linear decision boundary land, right? We are still a linear classifier, roughly. So we're going to move to a nonlinear one next class, okay? And that's where you'll see the strength of support vector machine. So the story doesn't end today. Thanks.